Hello, I'm Susan Buchheimer. In this film, we're going to explore some of what we know about this amazing treasure all of us carry under our skulls and how we know about it. Neuroscience is the scientific study of the structure and functions of the nervous system. In this film, we will be concentrating on the brain. These microscopic cells, neurons, are the building blocks of the brain and form a communication network. Rather than approaching neuroscience by looking at individual neurons, my colleagues, graduate students, and I, here at the Brain Mapping Center at UCLA, look at how assemblies of neurons work together to form functional units. We can measure the brain's electrical response to a single event and see how it unfolds over a time scale of milliseconds. Measurements of evoked electrical responses are called event-related potentials, or ERPs. This is the PET, or positron emission tomography scanner. A positron, a positively charged electron, is attached to a molecule using a machine called a cyclotron, which is a nuclear accelerator. Tomography refers to making a picture, or tomograph, of specific slices of tissue. The blood carries the radioactive glucose throughout the body and into the brain. The colored areas show where there is more glucose metabolism taking place, indicating healthy brain tissue. In these PET scans, red indicates the most glucose metabolic activity, yellow somewhat less, green even less, and blue minimal. Contrast that to this one of a person with Alzheimer's disease, whose brain shows a dramatic decrease in the metabolism, indicating widespread death of brain tissue. Conversely, this PET scan is from a person with an aggressive brain tumor, and you can see that this area is receiving more glucose than it normally would. In fMRI, the F refers to functional. We scan continuously, taking a complete picture about every 2 seconds. With the invention of very fast MRI imaging in the early 1990s, it is now possible to take a picture of the whole brain in a second or two. We have looked at normal children and those with autism while they imitate facial expressions in others. Children with autism do not show brain activity in these mirror neuron areas even when they physically imitate the expressions as well as normal children. Imaging techniques such as the ones you have seen in this film are, on a daily basis, enabling us to probe and thus better understand the human brain. As the technology improves, we'll be able to explore the brain in much greater detail and use this knowledge to better understand brain disorders, to visualize the effects of interventions on the brain, and to tailor treatment strategies based on this knowledge.